We're going to take a couple notes on 5.6 and 5.7. We are going to look at the content and then we'll do the examples in class tomorrow. So the first thing I want you to look at is this function. F of x is equal to 1 over x minus 1. If we look at this function, we have a couple things to notice. The first is that it is concave down from negative infinity to 1. So that means this left side of my graph is concave down. On the right side, from 1 to infinity, this function is concave up. I don't actually remember if we have ever defined these things in, like if we did it in pre-calc, but we're going to define them now anyway. So concavity, what does it mean to be concave up? I'm going to give you the calculus definition first. Let f of x be a function whose second derivative exists on an open interval I. On an open interval I. We can say that the function f of x, this graph, is concave up. So now we're going to focus on this blue section of this graph. It's concave up if the derivative on that interval is increasing. And then we can say f of x is concave down. This is the purple piece, concave down if, you guessed it, the derivative is decreasing. Let's look at what this means in our drawing one more time. Okay, we're going to focus on the blue half, concave up. If we consider the slopes of the tangent lines here, so a super negative slope up here, right? Super, super negative. And as I go from left to right, look at how these slopes are becoming less negative. Becoming less negative. They are increasing. If I look at the left part of my graph, where it's concave down, we have a very slightly negative slope, less negative, or excuse me, more negative, even more negative, a super steep negative slope. They are becoming more negative. These slopes are decreasing here. This is super important. If the function is concave up, its slopes are increasing. If the function is concave down, its slopes are decreasing. If we look at another just like simple example, here's a parabola. This function is concave up everywhere. Notice these are negative slopes, but they are becoming less negative. The slopes are increasing, they are becoming less negative. And as we round the corner, a very slight positive, more positive, even more positive. It's easy to see on this right side that these slopes are increasing. On the left side, the slopes are increasing, but it's maybe less intuitive because what's happening is that they are becoming less negative, which means they are increasing. So let's connect this then to our second derivative. Before we get there, I want to make one small reminder of what we took notes on last time we were in class. And that was, if the derivative of a function is positive, then the original function is increasing. And if the derivative of a function is negative, then the original function is decreasing, right? We know this. This is from our last notes. This is technically like 5.3. So now let's take in the second derivative. If, let's say, the second derivative is positive, that means the rate at which our slopes are changing is increasing. Positive. That means our derivative is increasing. And notice, if our derivative is increasing, that means our original function is concave up. So I'm going to write that here as the test for concavity. If the second derivative of a function is greater than 0 for all x in some interval, then the graph of that original function is concave up. Because if the second derivative is positive, that means the rate at which the slope of the tangent lines is changing, right? It's a derivative of a derivative. The rate at which the slope of the tangent line is changing, it's increasing, which means the function itself is concave up. And then we can say the kind of, not opposite, that's the wrong thing. We can switch it up to be concave down. If our second derivative of our function is less than 0 for all x in some interval, then the graph of our function will be concave down. Two definitions for you. The first is the definition of a point of inflection. A point of inflection is a point or an ordered pair. Sorry, a point of inflection is an ordered pair where the graph changes concavity. The graph changes concavity. So either going from concave up to concave down. So here's a function, right? That's like a cubic function that's falling. Notice it's concave up on this left side, but it is concave down on this right side. That means this point right here is a point of inflection, a point where the graph changes from concave up to concave down or concave down to concave up. And if we are changing concavity, concave up, our second derivative is positive. Concave down, our second derivative is negative. Well, if it's changing concavity, then must mean that our derivative of our derivative, that was a bad way of saying that, then the second derivative has to be equal to 0. Because if it's positive on the left and negative on the right, in between, it would have to be 0. The point of inflection theorem says if some point C, f of C, is a point of inflection, then either the second derivative at that value C is 0, which is what I'm kind of showing you in this image, or the function is not differentiable. Or the function is not differentiable at x equals c. So if we actually zip back up to the top, this is an example. This graph that we looked at the beginning is an example where it's changing concavity, concave down, concave up. X equals 0 is a point of inflection, but there is no derivative here. The function is not differentiable at x equals c. We'll do some examples based around this, and I have one other theorem. The second derivative test is a way to kind of find maxes and mins without doing the first derivative test. If I know that sorry, I have to back up. I'm so sorry. I don't know why I didn't read this to you, because this is really important. Let f be a function such that f prime of c is equal to 0. That means c is a critical value. And the second derivative of the function exists. Okay, so c is a critical value. The derivative at c is 0. If the second derivative at c is greater than 0, remember that means that our function is concave up then I would say f of c is a relative minimum. How do I know that? Again, the second derivative is positive. That means our function is concave up. And if we already knew c has a slope of a tangent line of 0, then of course this needs to be a minimum. On the flip side, if our second derivative at that value c is less than 0, this means our function is concave down, then f of c will be a relative maximum. Concave down, and I already knew that this value of c is a critical value. The derivative is 0 at that point. All right, we will look at the examples of these in class on Thursday. I hope you have a lovely day.